At the same time that scientists were discovering that there were galaxies outside of the Milky Way, they also learned that galaxies in general are moving away from us. And so this lecture describes the two important research efforts that led to that understanding. First, Besto Slifer at the University of Arizona's Lowell Observatory in Flagstaff, Arizona, attached a spectrograph to a telescope and it was the first to observe the redshift of galaxies. And then Edwin Hubble at Caltech used the Mountain Wilson Hooker telescope to observe the distance and velocity of galaxies. So that was used to develop the relationship between distance and velocity, which ultimately led to the conception of the Big Bang model. So in the 19th century, astronomers had learned to attach photographic plates to telescopes. The eye is not a good image collector in the dark. It's very difficult to see things with your eye in telescopes. But astronomers learned that if they attached a photographic plate to the telescope, they could collect light for hours. And then here's just some images they developed. They're very impressive. This would be a spiral galaxy. Here'd be a giant cluster of stars and other nebula. So in 1910, Besto Slifer attached a spectrograph to the Clark telescope and a photographic plate below that. And this was a 24-inch diameter telescope constructed in the late 19th century. And I'd just like to play you this short video about the telescope. It's quite famous. It was used to discover what they thought was life on Mars.
In 1896, Percival Lowell commissioned a Cambridgeport, Massachusetts optics firm for the construction of a 24-inch diameter telescope. Famous for the creation of some of the largest refracting lenses of the 19th and 20th centuries, Alvan Clark & Sons produced the now famous Clark telescope. Over the years, the Clark would be used by Lowell during his study of Mars. That led to his controversial theory that the planet was home to intelligent life, as well as V.M. Slifer for.
So this is the spectrograph that Slifer attached to the telescope. And I'm imagining his photographic plate was here, but instead of an image, it divided the light into the spectrum of the sun or of the galaxies. And so he was able to observe the absorption lines. So here's another picture of his spectrograph. It was very advanced at the time. Here's the little eyepiece he was looking through in the last picture. So a spectrograph divides light, uses a grating to divide light, just like a prism, but with much finer detail. So this is a certain type of spectrograph called an Eschell spectrograph. And as you remember from a previous lecture, there's absorption lines in light due to gases absorbing photons at certain frequencies. And the reason they do that is there's energy levels in atoms of the electrons, and they only absorb light at the frequencies that excite the electrons to the higher energy level. So there's going to be these little gaps in light that comes through, like the hydrogen gas cloud that's around the sun. And so scientists can see those gaps. So here's an image from a spectrograph, and you can see that there's certain emission lines they know are going to occur, such as the H delta line, hydrogen gamma line, and so on. And so scientists can look at the shift in the position of the absorption line. They know where it should be based on the light from the sun or experiments in laboratories. And they can see that if it's shifted based on the Doppler effect, they know how fast the star or the galaxy is moving away from us. So nearby galaxies have redshifts in the range of 0.003. And the redshift is calculated as the change in wavelength. So this offset here divided by the absolute value of the wavelength. So 0.003 redshifts corresponds with a velocity of a galaxy relative to the Earth of 1,000 kilometers per second. So Besto Slifer showed that 21 out of 25 galaxies are moving away from us. The ones that are moving toward us are in our own local group of galaxies. So they're not expanding away from us as the universe expands. And one of those is the Andromeda Galaxy, which is in our own local group of galaxies. So here's the Milky Way. Here's the Andromeda Galaxy. You might also have heard of the Large Magellanic Cloud, Small Magellanic Cloud, and Sagittarius Dwarf Galaxy, which are actually visible in the night sky. And so in our own local group of galaxies, the galaxies are gravitationally linked, so they don't expand with the universe. So for example, the Andromeda Galaxy is supposed to crash into the Milky Way galaxy in several billion years. But here's our local group. There's clusters of galaxies in the universe, and the Virgo cluster, or the Laniakea supercluster now, as it's called, are clusters of galaxies that are near our galaxy, and they are moving away from us. So when Slipher or Hubble observed galaxies in these clusters, they were moving away from us. So that would be the 21 out of 25 that were moving away. The ones that were close to us might be moving toward us. So here's what Slipher concluded. Remember that other people had already thought that there might be galaxies outside of the Milky Way. But he said, it has for a long time been suggested that the spiral nebulae, or spiral galaxies, are stellar systems seen at great distances. This is the so-called island universe theory, which regards our stellar system in the Milky Way as a great spiral nebula, which we see from within. So he said, because of the great velocity of these galaxies, they must be outside of the Milky Way. That's what he concluded. He also found that galaxies are rotating by showing that the redshift on one side of a galaxy was different from the redshift or blue shift on the other side of the galaxy. But what was missing? Slipher did not know how far away the galaxies were, so he did not realize there was a relationship between velocity and distance. But Henrietta Leavitt had found a method to determine the distance to galaxies, and those were Cepheid variable stars, which pulsated at a rate that indicated their brightness. So this was what's called a standard candle. Scientists know exactly how bright a star is in a distant galaxy, so they can know how far away that galaxy is from us. And there was an astronomer, a very famous astronomer named Edwin Hubble, and he had the best telescope, way better than Slipher's telescope. It had 24 times the magnification of any previous telescope. It had a 100-inch mirror, and so he was able to observe galaxies and the Cepheid variable stars in galaxies much better than Slipher could with his telescope. So Slipher discovered redshifts, but Hubble put together the idea that the galaxies, there was a relationship between the velocity and distance of galaxies. So here's an example of a Cepheid variable star. On December 17th, it's this bright. Then you can see that it's getting brighter. So this would be fairly easy to observe. You could look at the galaxy over time, maybe over several months, see how fast the pulsation rate was, maybe of a star right here, and then from that, determine the distance of that galaxy from us, and then from the redshift, determine the speed of the galaxy moving away from us. So this is a graph of galactic redshifts and distances. So the distance comes from the Cepheid variable stars. The redshift comes from the redshift. And so the redshift is related to the speed, kilometers per second. And you can see in this graph, the units are kilometers per second per megaparsec. And a megaparsec is 3.3 million light years. And so the Hubble constant, and you might not understand this, is just the slope of this line. It's the velocity of the galaxy over the distance of the galaxy, which is kilometers per second per megaparsec. So it was actually Lemaitre who figured out that there was a relationship between velocity and distance, and he's the one who discovered the Big Bang. You'll learn about him in the next lectures. Well, Hubble made a mistake. He did not realize that the Cepheid variable stars in distant galaxies were different from the Cepheid variable stars that were observed by Henrietta Leavitt in our own galaxy. Thus, he thought the galaxies were about 5 times closer than they actually were. And this threw off the Big Bang calculation of the age of the universe by 10 times. And then in the 1950s, scientists figured out that the correct Hubble constant was between 50 and 90, not 600 like Hubble calculated. And so with a correct Hubble constant, the age of the universe is calculated as 13.7 billion years old. And scientists argue over whether it's 72 or 68. There's two different sources of measurements. One indicates 68, one indicates 72, but both of them lead to a universe that's approximately 13.7 billion years old, which is older than anything in the universe.